Okay, in this particular exercise, we're going to be looking at simple harmonic motion again. In this case, we're going to be looking at conservation of energy and what conservation of energy can tell us. The problem is a 45-gram object is connected to a spring, has a force constant of 40 newtons per meter. It oscillates with an amplitude of 7 centimeters on a frictionless horizontal surface. Find the total energy of the system and find the speed of the object when its position is 1.30 centimeters. And of course, we'll let 0 centimeters be the position of equilibrium. Of course, we want to remind you that we are going to consider the mass spring system as an isolated system. That means that energy is conserved within that system since nothing acts from the outside, and energy cannot go past the boundary or come in through the boundary. So the energy of the spring mass system remains a constant. What is the maximum potential energy of a spring with amplitude 7 centimeters? Speaking, of course, of this spring, how do you calculate that maximum potential energy? Of course, the maximum potential energy is 1/2 Ka squared, where it reaches the maximum amplitude, and that's given by A. And we're told that that's 7 centimeters. So we can calculate what our maximum potential energy is, and it is 9.8 times 10 to the minus 2 joule. What is the conservation energy equation applied to the mass spring system? Well, since we know the maximum potential energy, that is the total energy. And that is going to remain constant. That means any change in potential energy is offset by a change in kinetic energy. So whatever the changes occur must be 0. And so we have that the change in potential energy plus the change in kinetic energy is equal to 0. There's another way to look at this, and that's to consider that whatever the potential energy is plus whatever the kinetic energy is, that must be equal to a constant. That has to equal that 9.8 times 10 to the minus 2 joules. So we can say that the kinetic energy plus the potential energy equal to the total energy, and we can give the detailed equations for both cases. If we look at the bottom one, 1/2 Kx squared, whatever the position is away from equilibrium, plus 1/2 mv squared, whatever the velocity is at that position, that those two energies must sum to equal the 1/2 Ka squared. And we can solve for v squared, and we have that v is equal to 0.21 meters per second. End of problem.